Good evening, everybody. Today I'll be talking about one of our recent works in which we observed a low energy plasma like Raman mode in palladium ditelluride. So, this study basically combines Raman spectroscopy, DFT, and then memory function formalism for the theory part. Uh, so, since it's a short talk, I'll first summarize whatever is there in this work, and then later we'll go to the details. So, if you see the title, there are four keywords. One is plasmons, which are collective oscillations of electrons in the material, and the other part is palladium ditellurate, which is uh, a tilted Dirac cone material, and means it's an exotic material of late. And then the third part is the memory function formalism, which is a powerful technique for studying different kinds of transport, and it's also useful for studying modeling Raman response of systems, and of course Raman scattering, which is the backbone of our study. And it is a beautiful tool that you can use to study several modes uh, in materials. So I'll start with a very small introduction for what are tilted Dirac cone materials, uh, like for the advantage of the audience, because these are materials which are, like, you can say, cousins of graphene, which has upright Dirac cones, but in these systems the Dirac cones are tilted, like, and that leads to this is the eigenvalues, and then you see there is an extra term, and yeah, this is the extra term that comes. This is the tilt term, and that is having this tilt velocity, and there are different ways of modeling this tilt, and there are different origins of this tilt. The tilt can come by disorder in the system or strain in the system, but the simplest way of modeling it for a theoretical perspective is you take like you allow next nearest neighbor hopping, and because in graphene the next nearest neighbor, like, you have two kinds of unit cells, and then the next nearest is always going to be of the same type, so it's going to induce a diagonal term, and that comes in this tilt part. And based on how much the cones are tilted, you have three types of tilted Dirac cones materials. In the type 1, the cones are slightly tilted, and the Fermi surface, when you dope the system, is still an ellipse. It's still closed. And then for type 3 it becomes a parabola, and for type 2 it's a hyperbolic Fermi surface. So this is some very rudimentary introduction to tilt and in Dirac materials. And coming to the material that we studied, palladium ditellurate, it is this is the structure of it, and there are some details of space groups and points groups which I'll just avoid for the time. And coming to Raman scattering, like, one picture introduction to Raman scattering is, you have a sample, you shine some light, you collect the light back, and then see what all new modes you have got. So after this very small introduction, let me come to what we did. So we did some experiments. Some in PRL there is another group that does Raman scattering experiments. They did some experiments, and then they found some results that, like, uh, in low like this is the Raman scattering data for different temperatures, and there are two modes, phonon modes, that have already been reported, that is found in this palladium ditellurate. But as you decrease the temperature below the cryogenic temperature, like around 80, 180 Kelvin, you start getting a new broad third mode, and that becomes more prominent at very low temperatures. So at first we were wondering what can be the origin of this mode. Like, is it really a phonon mode? Is it a second order phonon mode which is more broader or something? So our first step was in trying to rule out the possibilities. So, like, here you can see in this low temperature this new mode is there. And so we did a density functional theory study, and then in that we found out that there are only two phonon peaks in the system, and the third is definitely not a phonon mode. And then it can also not be a magnon mode, because in this system there are no magnetic atoms. Both of them are they don't have magnetic moments in both palladium and tellurium. So then there is, I mean, it's like it's very probable that it can be a plasmon mode. So that's the assumption we started with. And we kind of tried to model it microscopically in some way and see whether it actually works through. And so that's what the model that we built is, like, since there is one this mode is emerging at 250 wave numbers, we assume that there is one plasmon mode in that wave number which couples to the electron. And then we modeled, if that hypothetical scenario existed, what kind of a Raman response will it give. So you do some calculations and get to this expression, which is the imaginary part of the memory function, and that actually gives you the Raman response. So the imaginary part of the memory function is the scattering rate, so of like the Raman scattering rate, and that is supposed to be linear in the regime where our experiments were performed. I mean, it's a very complicated function. It doesn't look like a linear function, but you just plot this, you see that it's at the regime at which we are interested. It's a linear function. At least it looks like a linear function. And then we did some phenomenology, and I'll just skip the max part, go to the nice pictures part. Yeah. So we took our experimental data and we saw whether we do the same memory function analysis, and we get the Raman scattering, whether our phenomenology matches with the microscopics of the theory. So here we see, like, this is the scattering rate as a function of the wave number. If you zoom in and see, there is this linear trend emerging for temperatures below 100 Kelvin, like at 10 and 50, where this new mode has appeared. And when this new mode was not there, like for higher temperatures, uh, there is some kind of a saturation pattern coming. So this basically is because when you have a phonon in your system, then also you'll have a linear behavior. But then when you approach the Debye frequency, the saturation trend will come. And if you see the Debye frequency for Debye wave number for this system, palladium date tellurate, from experiments, it's around 1400 Kelvin. Sorry, 1400 wave number. So this is very consistent with the low and the high energy behavior. But at low energy, the plasmon mode becomes the dominating scattering process. So then this linear behavior kind of survives, because there is effectively not a Debye frequency emerging in the system. So, and then this trend is also seen in the real part of the memory function, which is called the mass enhancement factor. And so based on our studies of experiment, DFT and theory, we kind of tried to decisively assign this mode as a new plasmon like mode, because we are not saying plasmon exactly, because we are just ruling out possibilities and then saying it's going to be a plasmon mode. So we are just being a little cautious and saying it's plasmon like. And I think that I'll end it there.
Thank you. Thank you. Questions? Yeah.
Yeah. Yes.
You told about tilted Dirac cone.
Yes. Yes.
So 2 years ago, we wrote a paper that when the Dirac cone just touches the bottom,
Mm.
so it even travels. So it is
Yes.
not Dirac cone.
Yes.
Are you familiar with that work?
Yes. You shared it with me 2 months ago when I visited IIT.
Okay.
Yes. Yes.
That's
Yeah. That's, but I mean, that's a very interesting thing. But in that work, you kind of take the value of tilt to be different at different points. That is kind of a little. I mean,
this paper is based on this work which came this year, and also for the all the simulations and everything that has been done.
The code is also open source, so for anyone if wants to look. The title that Sir announced was slightly different, but since the time was little reduced for the talk, I had to change a little bit and try to make it more focused. So it is the same talk. So the first is what and why. So what I'm talking about and why square octagon lattice. So let me introduce the lattice. This is a square octagon lattice. It has been uh, studied recently, firstly by Viplab Pal sir, and he has studied in terms of this topology, and this Nunes and Smith, they have studied in the context of superconductivity. The interesting thing about this lattice is that firstly it's a four-site unit cell, and it has a natural multi-band spectrum. That is, it has multiple flat bands and Van Hoek singularities and your Dirac crossings and other stuff. So like I said, it hosts the Dirac dispersants, multiple flat band structures, and other thing is that if you introduce a magnetic flux around these plaquettes, you can also tune the bands using that magnetic flux, which is what Viplab Pasar has done in his work. So the one of and the other thing is that you have this hopping from A to B, A to D. These are the nearest neighbor hoppings. Then you have one nearest neighbor hopping which goes out of the unit cell. That is in the top. That would be A to the C out of the unit cell, and this one would be the next nearest neighbor, which is inside the unit cell. So we are calling this A to B, A to D as T1, that is nearest neighbor hopping, and this AC would be your next nearest neighbor hopping. So since we also talked, the title also has this quantum geometry. I just give you a basic idea that a block band is not simply described by its energy but also by its wave functions. And as you change the momentum, you can your you this you also changes. And especially in multi-band systems, this quantum geometry becomes very significant. And I also show you the bands as well. And in superconductors, especially in superconductor in the flat bands, there you have very important significance of this quantum geometry as well. This again I will show in this one. So just to introduce the quantum geometric tensor, this is the form of the QGT. The first part is your standard. You simply take a wave function overlap, but since this contains all the phase and the other parts, we have to subtract this part to get the true final QGT. We all know about we have been using this QGT, but in the form of the imaginary part, which is called very curvature. But what we'll be focusing on would be the quantum metric, which is the real part of this object. Now this is what I'm talking about, the quantum geometry. You have this different bands, and like I said, it is tunable. So you can change the T2 to get uh, from this Dirac crossings to spacings to directly to flat bands. And these flat bands, there are two flat bands. One is at the endpoint, the band edges, another is at the center. And with changing T2, and I also wanted to emphasize this, that as we change the T2, you will see that around mu equals to 0 or some specific points, you will see that different bands are either coalescing or growing apart. For example, and this part is the quantum geometry, the plot. So if you see around m points, there are lots of band crossings. You see, therefore, you see there. That's why you see a very bright points, and around this gamma as well you see. But as you increase the T2, see this basically disappeared, but still m these endpoints still have this quantum geometry, and this will also come up in superfluid. This is the basic model that we use. We start with a basic H naught, the standard one. Then we add superconductivity and the Rashba. And the method that we use is Bogoliubov degen in real space. This one is the phase diagram where we plot u versus the mu. The mu is basically changing the band filling, where you span from band edge to the top, and you go through different band fillings like flat bands and other Van Hoek singularities and this stuff. So you will see that uh, at suppose t equals to 1, which had two flat bands, you will see that -2 and 0 has stronger pairing and quicker pairing about that. So these are the regions which are much easier to have superconductivity. These are the high DOS regions basically. This one I'm showing the critical temperature and with changing the nearest neighbor hopping. And the idea is that the TC shows a non-monotic dependence. So as you change the nearest neighbor, basically what happens is that you're changing the bands from less DOS to a more DOS regions, and so you see this kind of behavior. But for small u equals to 2, You also see that there is an increase in TC as well over here as you go to higher DOS regions. Next, the other interesting thing about this square octagon lattice is that superconducting domes. You usually have two domes in this one in the negative mu region, and that is the further one. So one of the things that we wanted to look was the robustness, or how much does this survive with Rashba or other stuff like T2 ones. Then this one you see that starting we see that there are two very separated domes, and of course it appears as expected around the high DOS windows. For example, this would be your around Van Hoves, and this one of them is a flat band. For weak pairing, it is more selective to the DOS, or for stronger pairing, it extends over a wider ranges. And also, this was also done by Nunsen Smith, that in order to get the two domes, usually you don't need to have two separate mechanisms. One single mechanism can give these two superconducting domes. This one is with Rashva, and this is much more detrimental than the other one. The negative dome more or less remains intact. However, the positive dome, it is possible that it can get completely completely gone by for certain values. So you only, and even then, even the positive dome is very strongly affected with the Rashva SOC. This one I won't go into much detail, but we are also looked into the Raspberry induced triplet pairing correlations in this one, which we get, and but we get the expected result that equal spin has the biggest contribution. Yeah, this one I wanted to discuss for a couple of seconds. That this one usually in super, when we do the superfluid stiffness, we usually take only the conventional part. But in flat bands, that thing does not work. So we also need to look up the geometric part. So for example, mu equals to 0, remember it was where we had a flat band. So there you see the geometric contribution is extremely high, and that's why you get those superconducting domes and peaks. However, 1 minus 1.25, that's a Van Hoek singularity region, and that's where you get this part. This one is other interesting, where we saw the both from the this conventional one, and as well as this same is superimposed over there as well. So you will see that when one of them completely goes away, that's why you don't have that's why you don't expect superconductivity in this flat bands. However, that comes completely from the geometric contribution of quantum geometry. However, I also want to mention that this work on quantum geometry has been very popular after the works of Paima Torma and her groups. Very so. Yeah, for material context, there are platforms like octagraphene as well. For example, this TMD48 Hecleites, and which has a much stronger SOC gaps. So that was one of the reasons we studied the Raspberry SOC. And yeah, thank you so much.
Thank you. Let's thank Ravi. Questions? Is there an easy way to see why the two domes are formed? Like a simple way to see?
So one of the reason is the density of states, right? So if you look at the band structure, yeah, I will show you so that one. I was showing this. Yeah, look at this as well. These are the same. I was showing the different domes as well, right? So if you see the lower dome that you see over here, the lower bigger dome that you saw, more stronger, which was due to these bands. However, it did not have over here anything, but then you had from upper bands.
So it's
Yeah.
just different bands.
We're looking into, the idea was to look into different bands, and how, for example, see, of course you cannot have a T2 equals to that high, right? However, you can have a material which has band structure analogous to this. There you can compare the superconductivity. That was the idea too. Yes. Yes. Yes.
No, I was surprised it went to 0 all the way.
That was due to the Rashba one, right? You were asking.
Yeah,
The Rashba one, yes.
Any other questions? If not, let's thank Ravi
Thank you.
once again.
Thank you so much.
And we will come to the end of